All right, we are now ready to start Chapter 2, now that we've finished up reviewing how to evaluate integrals using the substitution method. And Chapter 2 is all about using integration in different applications in the real world. And the first one we're going to touch on here is Section 2.1, which kind of plays off a concept that you learned back in Calc 1, and that's find the area between two curves. Now you have this graph here, figure 2.1. You may remember from Calculus 1 that when we find the integral from a to b of a function, it gives us the area between the x-axis and that function. If that area happens to be above the x-axis, it's positive. And if the area happens to be below the x-axis, it's negative. And we're going to extend that idea for this section. So our learning objectives, we're going to find the area between two curves when integrating with respect to x, but also we're going to do it with respect to y as well. So let's go ahead and talk through that. So now we're going to have two curves. We're going to have a f of x curve and a g of x curve. And for the sake of all our problems, we're always going to think of the f of x as the one that's on the top. So f of x is going to be the upper curve. And then g of x is going to be the lower curve. And we're going to use the same idea in that we can approximate the area between two curves by finding the area of a bunch of rectangles. Each rectangle has a length and a height, or a width and a height. So remember, the width we can think of as our delta x, and then our height, before our height was the function, it was f of x, but now it's the difference between those two. So if you take f of x minus g of x, that's going to give you the height of this. And then if you add up the area of all these rectangles, every single one, every single rectangle, you're going to get the total area between the two curves. And the integral that we would use in this case is going to be the one that you see here in Theorem 2.1. So it's going to be the integral from a to b, but instead of integrating f of x dx like we did back in Calculus 1, instead of calculating this, we're going to replace f of x with the difference between the top function and the bottom function. So we're going to use this integral right here. And well, you may be thinking, well, it's not always the case that you have one function always on the top and another function always on the bottom, and that's true. Sometimes it works out a different way. Sometimes you might have a function that's always on the right and another function that's always on the left. And in this case, it's still going to be kind of the same idea, but our rectangles, instead of them having a width of delta x, now they're going to be delta y. And then the dimension this way, the height, if you will, even though it's like a horizontal height, that dimension is going to be from subtracting the functions. Now instead of going the function on the top minus the function on the bottom, it's going to be the function on the right, which in this case would be the orange looking function, minus the function on the left, which is the blue function. So this is our, call this our right function, and we'll call this our left function. So u of y and v of y. And so when you go to look at the theorem, you'll see it follows that. It's u of y minus v of y. This is the right function. This is the left function. dy, and our limits go from c to d on the y-axis. If you look back up at the picture, you can see here this area in here goes from C to D. Okay, so we have that. We have these two theorems, which we're going to solve a couple examples now. This was just kind of our introduction video. Make sure you check out the next video and we will go over example 1 here.